Okay, so this is the first lesson for AP Calculus BC. And our first unit this year is going to be a short unit that we do covering the topic of limits. And although this is a relatively simple topic, I want to stress the importance of what we do in this unit. Really, everything that we do in calculus relates back to the idea of a limit. So this year, our primary topics are going to involve derivatives, integrals, and infinite series. And all of those things, when we look at them, you will see how limits are involved. And in fact, with a derivative, the definition of a derivative is a limit. With integrals, the definition of an integral is a limit. And when we're talking about infinite series, we're going to be talking about the limit as the term number approaches infinity. So the main idea here is, although this is relatively simple stuff, it's super, super important to understand the details of what we're going to be doing in this unit, just because we're going to see it throughout the year. Now, this first section that we're going to talk about today, I'm going to go through this relatively quickly. It's section 1.1 in your book, and it's just an overview of limits. So there's a lot of material thrown in here. And what I want you to realize is we're just looking at sort of the general understanding of limits. I'm not expecting you to be able to do every single type of limit problem that you're going to see yet. So keep that in mind. When you go through and you look at the homework, you'll see that with the homework, it's a lot of, kind of more general questions, very, very basic questions. And then as we go through the unit, we'll start to get into some of the more specialized ideas that we can start to encounter when we're dealing with limits. I'm going to show you everything because that's what this overview section is. It'll even get into some of those specialized sections, but I'm not going to go into the details of how all of those things work until we get into the sections that are really particularly focused on those types of limits. So for today, let's just, start by quickly discussing what the idea of a limit is. So in order to give you a visual representation of the idea of how we're going to use this first drawing that is on here is really displaying how we are able to find the value of a derivative by using a limit. So it's kind of the definition of a derivative. We're going to use this to find the slope of a tangent line. So we've got this function 0.1 e to the x that's been plotted down below here. And you notice that there's 2 points that they're referencing the point P and the point Q. Point P is fixed at the point where x is 1. Point Q is actually going to be a point that's moving from 4 to 3 to 2 to 1.5 and so on, getting closer and closer to x is equal to 1. Okay, so it says draw the secant lines. And then what we're going to get is we're going to get a graph that's going to kind of show what's happening as Q is moving towards the point P. So I'm going to start this, and then I'm going to show you a finished version of this so you don't have to watch me graph this whole thing. But we're starting at the point where x is equal to 1. This would be the point P. And then the point Q is going to start out here where x is equal to 4, somewhere about right here. So that's the point Q. And you can see right now those 2 points are very far away. If I drew a secant line between those 2 points, it would not at all resemble what the tangent line looks like. So as the points get closer and closer together, what you're going to see is the point Q is going to start to approach the point P, and the secant line between those 2 points is going to start to look like the tangent line at the point P. So here's my completed sketch, and this is just a rough sketch. We're just trying to get a general idea. So I didn't try to do this to make it look, perfect or pretty or anything like that. I just wanted you to have the general idea. The point P and the point Q, if you move along this 0.1 e to the x function, and as I move to the left along that function, you can see that point Q moving closer and closer to the point P. And you can see my secant lines are starting to resemble what the tangent line would look like. Okay, so let's go back over to another example of this. It says, find an equation of the tangent line to the parabola y equals x squared at the point 1, 1. So some of you may know how to take a derivative, and this might be something that's very, very simple to you. Keep in mind as we go through this, we're trying to get the idea of a limit. We're not trying to use derivative shortcuts right now. We're just trying to do the absolute basic level understanding of how to find a tangent slope. So when we find the equation of a line, we always have to have 2 pieces of information. We need a point and a slope. You can see the point is given. The slope that we need is the slope of that secant line PQ. And if I were to find that slope, it would be the change in y over the change in x. So the change in my y values is x squared minus 1. The change in my x values is x minus 1 when I'm using that segment PQ. Okay, so obviously right now, Q is pretty far away from the point P in the way that this is graphed. What we want to do is we want to make Q get very, very close to the point P. So what I'm going to do is I'm going to rewrite this as the slope of the tangent. And the way we're going to find that is by taking the limit as x approaches 1. We want that general coordinate of Q, we want that general x coordinate x to approach a value of 1. So I'm going to take the limit of this expression. And the way I'm going to take that limit is now I'm going to try to plug in what we call direct substitution. I'm going to plug in 1. And when I do that, you can see I get 0 over 0, which is an indeterminate form. So this is one of the types of limits that we're going to have to learn how to solve. To solve a limit like this, it's pretty easy to do by factoring. You guys did this when you did removable discontinuities back in Algebra 2, and you did this in pre-cal as well. So if I factor the numerator, I'm going to get x minus 1, x plus 1. You can see the denominator is still x minus 1. And now I can cancel out these x minus 1s. And what I end up with is the limit as x approaches 1 of x plus 1, which would just be equal to 2. So that's going to be the slope of my tangent line. So the two pieces of information that I needed, I've got my point, and now I've got my slope. So to find the equation of the tangent line, I'm going to write out the fact that this is my tangent line. I'm just going to use the point slope formula. So the point slope formula is the most basic equation of a line that we have, because if we have these two pieces of information, we just plug them straight in. Y minus y1 is equal to my slope times x minus x1. And I'm just going to leave the equation in that form. I'm not going to try to put it into slope-intercept form or do anything else with it, because this is the form that we're going to want to use in this class really moving forward, because when we get into Taylor series in the second semester, you'll start to see how this form is actually really useful. The nice thing from a line perspective about this form is that I can still reference my point of tangency. I can see it's at the point 1, 1. If I go through and solve for y and get it into slope-intercept form, now I no longer have that easy reference to my point of tangency. Okay, so let's move on here and take a look at some things graphically. So this says use a calculator to help you guess this limit. It says take the limit as x approaches infinity of this function. So taking the limit as x approaches infinity just means as x gets very, very large, what does it look like this function is approaching? And in reality, what we're doing here is we're finding a horizontal asymptote. You guys did that back in Algebra 2. Again, some more in pre-cal. May not have discussed it as a limit, but a horizontal asymptote actually is a limit. So what I want you to do is go ahead and graph this on your calculator and see if you can come up with a solution. You can just pause the video here while you do that, and then unpause it when you're ready to check your solution. So what you should have found is that this is 3/4. And if we went through and we solved for that horizontal asymptote, it would in fact be 3/4. Okay, so let me show you another one here. It says find the limit as x approaches 0 from the right. So if you look at this notation where it's got the 0 with a plus, that means we're taking what we call a one-sided limit. We're taking the limit from the right-hand side. What value is the function approaching as we approach x equals 0 from the right? And then over here, we've got this 0 with a minus. That means we're taking the one-sided limit, the limit as x approaches 0 from the left. Okay, so let's take a look at the graph of this. So when I graph this, here's my function, 1 over 1 minus 2 to the 1 over x power. I'm just going to graph this right now in the standard form, and this is what it looks like. And you can see that something weird is happening at 0. Even with this TI-84 plus, I can see something strange is happening, but even with the limited number of pixels, I can tell something's going on there. So it's not really that good of a view of it right now. So what I'm going to do is I'm going to zoom in. I'm going to hit zoom, and then number 2 is zoom in. And I'm just going to zoom in on the origin so I get a better view of this. And you can see what actually happens there is we've got a jump discontinuity or a step discontinuity when we hit 0. From the left, it looks like we're getting very, very close to 1. And from the right, it looks like we're getting very, very close to 0. Okay, so I'm going to go back over here. And we said from the right, it looked like we were approaching 0. From the left, it looks like we're approaching 1. Now, the most basic form for the definition of a limit is going to be the fact that in order for a limit to exist, my left-hand limit and my right-hand limit are going to have to be equal to the same value. In this case, obviously, they're different. So over here, when you see this notation, x approaching 0, that means we're taking the overall limit at that point. We're no longer interested in one side or the other. We're interested in overall at this point, what's the general trend or what's the behavior of this function as we get close to 0. Since we have that inconsistency from the left-hand side and from the right-hand side, that means our limit fails to exist. So we're just going to write DNE to represent that limit does not exist. Okay, so let's move on to the formal definition of a limit. When you get into the formal mathematical definition of a limit, you get into a lot of really more technical jargon. If you're going to be a math major, this is something that's going to be very, very important to you. If you're somebody that's just going to take calculus because you have to, and as soon as you're done with it, you're not going to use it anymore, you're not going to be as interested in this. But I'm going to go through it for everyone because there are people in here that are going to be math majors or maybe physics majors or things that are heavily involved in mathematics where they really need to understand what's going on behind the scenes when we're solving a limit. So the formal definition of a limit says the limit of f of x as x approaches c equals L if we can make the value of f of x as close to L as we like by taking x to be sufficiently close to c, but not equal to c. So it's quite a mouthful, but in reality, what we're talking about is the left-hand limit and the right-hand limit being equal to the same thing. So in mathematical shorthand, that'll sort of explain what this graph or this diagram that we have over on the right is showing. So there's a lot of shorthand notation in here, but it says the limit as x approaches c of f of x is equal to L, and then the IFF means if and only if, and that upside down A. So it says if and only if for all epsilon greater than 0, and then we see that backwards E, there exists a delta greater than 0 such that the distance between x and c is less than delta, and that implies that the distance between our function and the limit is less than epsilon. So basically what that's saying is as we get closer and closer to our x value from both sides, we're going to get closer and closer to our limit value from both sides. So if you look at the diagram, you've got the delta here representing the distance we are from c. We've got this epsilon representing the distance that we are from that L value. And you can see as we move along this function from both sides, we are approaching that same value, that same function value of L. So that's really what the formal definition of a limit is. Now, if you go into mathematics in college, you're probably going to have to write proofs for limits. We're not going to do that in this class, but there is a way to do it. It's not that difficult to do, but you have to sort of work things backwards to be able to work out the limits. There is a section in your book where they go into writing out proofs for limits. And if you want to read through that, you can, but we're going to skip over that section because for the majority of you, writing proofs for limits is not going to be something that's very useful. Okay, so we had that formal definition of a limit. That's not really the one that I want you to memorize. The one that I really want you to remember, and this is the one that you're going to use, is the one that I have down here in the box below. There's going to be a lot of times throughout the year where I'm going to ask you to justify why a limit exists. And this is exactly what I'm talking about when I ask you to justify. So we're saying the same thing as the formal definition of a limit in a much more simplified way. It says the limit as x approaches c of our function is equal to some value L. if and only if the left-hand limit at C is equal to L and the right-hand limit at C is also equal to L. So essentially, if the left-hand limit and the right-hand limit are equal to the same value, then the limit at that point is going to exist. It's going to be equal to that value. Okay, so like I said, keep that in mind. What I've got circled in red there is super, super important because you will definitely have to use that moving forward in terms of justification for why does the limit exist or why does the limit not exist. It all has to do with those one-sided limits. Okay, so we can see examples here of a limit existing. So we've got three different functions that are plotted here: f of x, g of x, and h of x. And if you notice, we've got graphs that are all slightly different. But what's important to see is what's happening as we're approaching 1 on each one of these graphs. If I were to take the limit as x approaches 1 on this first graph, I'm approaching a function value of 2. There is a hole in the graph at that point, but what's happening, what the function value at 2 is, does not matter when it comes to the value of the limit. The limit is just basically saying, what's the trend of this function, essentially? And the trend is, from the left side and the right side, I'm approaching a value of 2. Same thing on the next one. You can see that from the left and from the right, I'm approaching a value of 2. Now notice this time we've got this point discontinuity where this point has been sort of removed from the rest of the function. That doesn't impact what the limit value is. The limit value is still 2. And then the last one here, we've got a continuous function. Same thing. Now we're approaching a value of 2. Continuous functions are always the easiest ones because you can just look at the function value and that's the limit value. The main idea is it doesn't matter what the value of the function is at that point. It just matters what is the function trending towards from both sides when I take the limit. Okay, so now here are some examples where the limit fails to exist. So you can see, again, sort of three different scenarios here. We've got this jump discontinuity or step discontinuity happening in my function, but you can see that my left-hand limit and my right-hand limit, they're not matching up on these graphs. So for that first one, my right-hand limit would be 3, my left-hand limit would be 1, and my limit wouldn't exist. And same thing, all three of these actually have the same left-hand limit and the same right-hand limit. So we've got this step discontinuity. It doesn't matter what's happening at the point. You can see we've got three different values here. This one, those are both defined. This one, there's the third one, there's no function value defined because those are both open circles. So even though the function value doesn't exist or it is defined at a point, it doesn't make a difference in terms of what's going on here. For all three of these, the limit would fail to exist. So you would write D and E for all of those. Okay, and then we've also got a few limits here where we're just going to talk about the idea of direct substitution. Direct substitution, when we have a continuous function, the limit value is just going to be equal to the function value. And that's what this is saying. So the limit as x approaches a of f of x is equal to f of a when we have a continuous function. So for example, on this first one, we've got x squared minus 1 over x minus 1. If I take the limit as x approaches 1, in the numerator, I'm going to get 0. In the denominator, I'm going to get 2. That just gives me a limit value of 0. For the second one, we've got 5x squared minus 6. If I plug 1 into that, I'm just going to get 5 minus 6 or negative 1. Okay, so we also are going to look at, in this unit, we're going to look at the idea of infinite limits. And the function 1 over x squared is one that we're going to look at a lot. So what I'd like for you to do is just pause the video, take a second, and just do a quick sketch of what you think 1 over x squared looks like. And if you need to graph it on your calculator, go ahead and do that. But you should get to the point where that's something you can plot very, very quickly without looking at the calculator. So go ahead and pause it, sketch it, and then I'll show you what it should look like. Okay, so when you are looking at graphs like this, one thing that I want you to consider is that we have a lot of prerequisite information that I'm expecting you to know in this course. And one of the things that I'm expecting you to know is how to graph rational functions. And so things like horizontal asymptotes, vertical asymptotes, those are all things that you did in Algebra 2. Those are all things that you should be able to recall very quickly. And that's part of the reason that we have a prerequisites test coming up fairly quickly, is that I want you to actually take a little bit of time and go back and review those things because we need to be able to recall them for problems like this. So 1 over x squared, I just want to actually graph this for you so you can see that when you're sketching these, I'm not expecting you to do a perfect graph. I'm just trying to get a general idea of what your thought process is. So if I were to graph this, I already know what this one looks like because 1 over x squared is one that I use a lot. But I know there is a vertical asymptote at 0, and there's also a horizontal asymptote at y equals 0. So from both sides of 0, I'm approaching infinity. So it says, what are the one-sided limits approaching? They're approaching a value of infinity. And notice on my graph, I didn't really label the x and the y-axis. I just have a little sketch there. And it's just something that's basic, that's showing what's happening in my head or showing what's happening within my reasoning to allow me to find that value. Okay, so we've got a few examples here that are just graphical limits. And this is a lot of what you're going to see in your homework today. So we've got this piecewise function, g of x, that's been plotted, and there are 6 limits here that I want you to try to solve. So go ahead and pause the video, solve these 6 limits, and then when you unpause it, we will take a look at the solutions for this one. Okay, so for those 6 questions, remember, we're just looking at one-sided limits. So more than anything, if you understand the notation for this, it's pretty straightforward. You can see when we approach 2 from the left, we're approaching 3. When we approach x equals 2 from the right, we're approaching a y value of 1. And then those 2 limits do not match up. So we know the limit fails to exist or does not exist. When we look at x is equal to 5, from the left, we get 2. From the right, we get 2. So overall, the limit as x approaches 5 is also equal to 2. Okay, so last thing here, we've got a few problems where there's just sort of some mixed practice with limits. And what I want you to do is I want you to try to solve these. Now, this is getting more into what's going to be within this unit. But really, these are things that you probably have seen before in terms of how to deal with them algebraically or graphically. So the first 2, you should be able to use some basic algebra to solve those out and find the limits. The last 2, and actually I think there's 5 down here at the bottom. The last 5, those are ones that you should be able to solve graphically. So I want you to take a few minutes and I want you to try to solve out those 7 limits. The first 2 using algebra, the last 5 either by thinking about the graph or by actually sketching the graph. So take a couple of minutes, solve those out, and then when you come back, we'll talk a little bit about the solutions for those. Okay, so for these first 2, it's very similar to the one that we looked at the beginning here when we were looking at the equation of the tangent line. All I did was I recognized that I had the form 0 over 0 if I did direct substitution. So to solve that, a lot of times factoring will help. And that's what I did is I factored the numerator, and that allowed the x minus 1s to cancel out. And now that's essentially the limit as x approaches 1 of x plus 1, which gives me a value of 2. Now, if I look at the next one, we could factor the next one because technically we do have the difference of squares, but it's actually easier on this one to expand things out. But the first thing is I always want to try direct substitution. If I plug 0 into the numerator, I'm going to get 9 minus 9, and then I would have 0. And in the denominator, I'd also have 0. So another indeterminate form. So I expanded out my numerator, and when I expanded that out, what I ended up with here, you can see these 9s canceling out. This 9 and this 9 are going to essentially add up to make 0. So I end up with 6h plus x squared divided by h. The h can divide out of both of those terms. So this simplifies down to 6 plus h, which is just 6. If I were to graph that, what that means is as I approach 0 from the right and from the left, my function is going to be approaching a value of 6. And then these last 5, like I said, these are just graphical limits. So again, a little bit of practice with some of that prerequisite material. So 2x over x minus 3 is a rational function. We've got a vertical asymptote at x is equal to 3. And really what we're interested in, because we're looking at the limit as x approaches 3, is what's the behavior around that vertical asymptote. And you can see from the right, I'm going to get infinity, and from the left, I'm going to get negative infinity. And then the same thing down below. We've got the secant function. So that is a graph that you should know, or at least know how to create. Remember, you can always just graph the cosine function. And from that cosine function, you can figure out where the vertical asymptotes are. And then you can sketch the graph off of that. But you can see we get negative infinity and infinity. And then the log function, the natural log function, is one we're going to use all the time in this class. So if you don't remember what that graph looks like, graph it on the calculator or sketch it out, but that's one you absolutely need to know. You've got to be able to graph that one, and really that's one you should just be able to look at and answer. And if you can't do that now, that's fine, but that's one that kind of put a star next to that one. That's one you're definitely going to need to know really, really well moving forward in this class. Okay, so that's everything on our introduction to limits. And like I said, these problems, especially this page where we've got these 7 problems, I'm not going to ask you to do a lot of this type of stuff yet. But as we go through this unit, this is essentially what we're going to do, is we're going to figure out how do we figure out the behavior of a function just by solving the limit. So remember, solving a limit, quote unquote, solving a limit is trying to figure out what is the value of the function, or what value, let me restate that. What value is the function approaching as our x value or our variable value approaches some specific point. And if we get the same behavior on both sides, the limit exists. It's equal to that value. If we get behavior that's not consistent, then our limit fails to exist.